Okay, hello everybody. I wanted to kind of provide a video of the Lagrange method. I had one previously years ago, but Google cut it short, so I'll re-record it um, for this class, and I'll go over problem one from exam one because it kind of involves a lot of good steps and edge cases that still work well with the Lagrange method. So what I'm going to do is just to remind everybody what the Lagrange equation is. So it is d dt of our kinetic energy with respect to the velocity, and these are full derivatives right here. This is a full derivative, that's a partial derivative, okay? Minus the full derivative of the kinetic energy with respect to position, um, plus the derivative of the potential energy with respect to position, plus the derivative of the energy lost to damping with respect to the velocity. And then for right now, it's just equal to zero. Eventually it'll be equal to the external forces. Right now, it's just set it equal to zero, okay? And I know this is a lot of equation, but I do like the Lagrange method because we can break up this seemingly complicated equation into a process that is very easy to implement. And anytime you have a process that you can break down into little steps, it it really does reduce the mental load on you when you're solving these problems. There's not a lot of guessing or creativity involved. It's just something you do. Now, it does require a lot of practice to get good at it. So you can't just watch this video and all of a sudden be good at it. But please use this video when you're doing problems if you, um, kind of need a little help reminding what the steps are and how we apply them. Okay, so that's a Lagrange. And what I'm going to do is I'm going to list the steps. It's 13 steps, which sounds like a lot. But like I said, this is about breaking problems up into smaller bits and pieces and having a process that's relatively robust. So I'll list the steps, and then we're going to go through these. We're going to go through these steps. Okay. So in step one, the first thing we're going to do, step one, is we are going to draw the displacements. Okay. And after we draw our displacements, we are going to list the degree of freedom. Okay, so I'm going to go through this whole problem after I get done listing things, but for a couple of them, I'll show some examples of what I mean as I go through these steps, okay? So here's our system we're trying to get the equations of motion for. I've already provided a displacement of the whole system, but next we need to actually look at our displacement. So we're provided theta, and then we have another displacement. So here's a displacement that's relevant x, and then there's also a displacement that's relevant y. Here's another displacement. It's the same magnitude x just because these are all the same lengths for this problem to make it easier for the exam. But it doesn't really matter if they're different lengths. We would call it x1, x2, x3, etc. But in this case, there's really only one displacement we care about, x, and that y, and then here's another x. So we've drawn our displacements, and we would list our degree of freedom. So we might say theta is equal to theta, and theta dot is equal to theta dot. Okay. So those are the first two steps. And these are, I know they sound small, but they're really critical steps because this is how we're going to start getting the geometric relationships between the displacements that matter and our degree of freedom. Because we can't always count for all of the displacements to be in the degree of freedom. Okay, that brings us to step three. Okay, and that is we're going to get the geometric relationships between our degree of freedom and the displacements. Okay, so we'll get those geometric relations. So an example might be x is equal to L sine theta. X dot is equal to L cosine theta, theta dot. And y is equal to L times 1 minus cosine theta. And that's all the relationships in this particular problem, but problems might have more or less. But we list out what those relationships are. That takes us to step four. And step 4, we are going to list the energy sources and sinks or drains. So, for example, that's what's kinetic energy, potential energy, and dissipative energy. So for our kinetic energy for this problem, we can see that we've got J, M1, M2, and M3. Okay. And we do the same thing for the potential energy. We see we have a spring. Mass 1 will be a negative potential energy. Mass 3 is a positive potential energy. And our dissipative is going into C. Okay, so we just list those. We don't worry what their form is yet. We just make sure we've got that accounting. Okay. And then step 5 would be list the energy equations for each source and drain. Okay, so for example, you might have I'll not do kinetic energy. I'll do the potential energy for the spring, right, is equal to 1/2 kx squared. Okay, we go down that whole list. Do m1 is equal to, and the kinetics. We go down the whole list. I'll do that later when we go through the whole problem. But that's going to lead us to step 6. And step 6 is we're going to use step 3 relationships. So that's relationships of our geometric relationships. To put the energy, right, to go to the energy equations in terms of our degree of freedom. Let's let the degree of freedom. So that would be is equal to 1/2 k, and then x is equal to L sine theta. That's squared. That's 1/2 k L squared sine squared theta. Okay. So now we have the energy, and we convert it into the relevant degree of freedom. Okay, that's a really big important step for the Lagrange method. Okay. So I'll erase this. We're going to do it again later. I just want to list through the steps now. That takes us to step 7. Is we're going to go and apply the Lagrange equation. Okay, so the first step of the Lagrange equation is we're going to take the derivative, the full derivative of the kinetic energy terms with respect to the velocity. And Q dot is just whatever the degree of freedom is. Okay. Step 8 is we are going to take that earlier result, and this is supposed to be a partial, t of dt dq dot. We're going to take any of these results and apply the second derivative to. Okay. Step 8 is we're going to take the kinetic energy and get the partial with respect to position. And for this class, this should typically be 0 for the problems that we're going to deal with in this particular course. But for other systems, that might not be 0, especially nonlinear systems. Okay, but we don't deal with nonlinear systems. Okay, oh, this is supposed to be step 9. So step 10 is we're going to take the potential energy with respect to the position. And then step 11 is we're going to take the damping energies with respect to velocity. And then step 12 is we're going to collect the results. And step 13 is from these collected results, we're going to get the equivalent masses. Make that a little neater. Get MEQ, CEQ, KEQ. Okay. So those are the steps we're going to take. So let's go through this particular problem and do all those steps, ideally together, but at least this way you have a video of them. Now remember, this is something you have to practice to get good at. And if you don't practice, it's hard to have it in a usable state, okay? So our step one was draw our displacement. So we have your system drawn here. Let's go and give it the initial locations of those arms. Okay. Let's erase those extra little things. Okay. And then we have displacements that we can identify in this system is this is moved by x. And I'm just going to call each one of these x in this case because they're all the same length. But if you had different lengths and different magnitudes of displacements, you might call it x1, x2, x3, etc. And then for these ones right here, these masses undergoing rotation, we're also going to be interested in this potential energy change. So we'll also list y. So those are our displacements, and we already have our degree of freedom listed, okay? That takes care of step one. Not hard, but it's something you definitely want to practice, okay? That takes us to step two. Let's start degree of freedom. Theta is equal to theta. Theta dot is equal to theta dot, okay? Now step two. Now we're on step three. We're going to do the geometry and trig to get displacements in terms of our degree of freedom. So we have a displacement x up here, and that equals L sine theta, and then a velocity of x would equal L cosine theta, theta dot. Is if you take the derivative of this with respect to time and apply the chain rule. And we also have y is equal to L times 1 minus cosine theta. Okay, we've done that in class a bunch of times. So now we've finished step three. Step four is we're going to list the items that have different types of energy. Okay, so let me separate those. So in terms of kinetic energy, we can see we have J, this mass, and that mass. So J, mass 1, mass 2, mass 3. Now notice, I don't care what the form of this kinetic energy is. I'm just listing them so that I can go through and make sure I do my accounting. We have the potential energy. Okay, so we have the potential energy of the spring. And then these masses are undergoing rotation. So they're also going to have an impact on the potential energy. So we have K, M1, which in this case is negative because it's falling, and then M2, M3, not M2, M3. Okay, so that one's positive because it's rising up, where this one is rising down. So that's where that sign comes from. And then we have our damping, which is just coming from this single damper in this system, okay? So that takes care of step four. Now let's go to step five. And for step five, we're going to list all of those energies. So the kinetic energy for that J is 1/2 J theta dot squared. And then the kinetic energy for that mass mass 1 is 1/2 M1 x dot squared. Now, there's a couple ways to do this. You can either list all of them right away. I have a habit of going and doing this mixing step 5 and step 6 together as I do each one. I find that works better for me. So that's what I'm going to do because that works better for me. And oops, oh, rookie mistake. Now that I'm checking my work, if you have a mass that's rotating, like M1 here, I have this habit of running M1 x dot just out of habit because I do so many linear equations. And then once I start doing this step 6 where I put it over, I remember, oh, this is supposed to be theta dot. So this is actually 1/2 J for that mass 1 times theta dot squared. So if you have a point mass that's rotating, make sure you focus on its polar moment of inertia versus its linear mass. Okay? That makes a really big difference in how simple the Lagrange is. Okay? And then this one, it's already in our target degree of freedom, but I'm going to go and put J here. So that becomes 1/2 J, 1/2 M1 L squared theta dot squared. Okay. Like I said, it's pretty common for me to, out of habit, put in m2x dot squared or things like that. And it's really important that I come up with a technique to stop that habit where I think about this and realize really I've got a mass that's rotating. So it means I want the polar moment over inertia. So that becomes m2l squared theta dot squared. The kinetic energy for that mass 3, which is rotating, is 1 half j mass 3 theta dot squared is 1 half mass 3l squared theta dot squared. Okay. And I know this is like really tedious, but that's what we want. We want processes that are robust and simple to apply, and that might mean they might be tedious because a tedious thing doesn't actually require a whole lot of thought if you've practiced enough. Now I can go back, and this is a good spot to check my work. Okay, what items have kinetic energy? Okay, there's this, mass 2, mass 3. Am I missing anything? Does the spring have mass? Does the damper have mass? Nope. Okay, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. That's good. Are these in thetas like they're supposed to? Did I apply rotation? Is this ml squared? Did I get the right L's here? Did I get the right M's here? Okay, things are looking good. So notice what I did. I stopped, I used my earlier work, and I checked my work because it's easy to kind of make mistakes, small mistakes, or been habits, like putting mx dot instead of ml or j theta dot squared for masses. So you want to pause and check. Okay, so now that takes care of our kinetic energy. Let's take a look at our potential energy. So potential energy at a spring is 1 half kx squared. So that's 1 half k times L sine theta squared, and that equals 1 half k L squared sine squared theta. Okay. And then the potential energy for that mass 1 is negative m1g times y. That's the change in height. Negative m1gl times 1 minus cosine theta. Because remember, I did all geometric relationships earlier, so I don't have to think about them anymore. Now I just have to apply them. And the potential energy for mass 2 is negative m2gy. Oh, this one's positive. Positive. That's another reason I check my work. You get in the habit, you see a negative before, you put a negative by accident. Anytime you have potential energy masses, you should be checking. So you saw me check and catch myself because I had a quick transcription error. So this becomes positive m2gl times 1 minus cosine theta. So you'll see me put the positive and the negative here to remind myself to check those values, make sure I've got the sign correct before I proceed forward. Okay? Because it's easy to kind of get in some sort of rhythm and make this mix. And now we got the damping. So this is cx dot squared. This is 1 half c times L cosine theta, theta dot squared. And this simplifies to 1 half cl squared cosine squared theta, theta dot squared. Okay. So that takes care of steps 5 and 6, which I kind of did in parallel. Now to make this easier for you to see, I'm going to consolidate these lines so that they're all one nice little column. Okay. So if I was on an exam situation or something, you would see me rewrite them someplace else. But I'm on a tablet, so I'm going to just erase and move things around. Okay. So there's that. Now the next thing to do is go down and start applying the Lagrange. Let's draw that line. Let's move this one up a little bit. Here we go. So the first step of the Lagrange is to take the derivative, the full derivative kinetic energy with respect to q dot being the degree of freedom, so in this case it is theta dot. And this just simplifies to j theta dot m1l squared theta dot m2l squared theta dot m3l squared theta dot. And then these aren't kinetic energies. So U is not a kinetic energy, it's a potential energy, so these are 0. Okay, so let's do the next column. And the reason I like this column system is it's kind of breaking up the work to make it kind of easier for me. So I'm only thinking about one thing at a time. So now I'm going to take the partial derivative of this earlier column. So this becomes j theta double dot m1 l squared theta double dot m2 l squared theta double dot and m3 l squared theta double dot. Okay. And let's go. That's the first part of our Lagrange equation. This next column is very easy for this particular course. It is the full derivative of the kinetic energy with respect to the displacement, which for the problems that we do are going to end up being zero. If you have some nonlinear systems, then it might not be zero. But we don't really deal with nonlinear systems in this course. So that one's always zero for this course. If you have something that's not zero, either we're doing a fun homework problem or if you're on an exam, most likely the common case is you forgot that these should be polar motor inertias. And if you put in the polar motor inertia form, then you don't have an L sine theta or cosine theta in there, just theta dot, and it comes out right. But if you, for some reason, left x dot in here, m x dot, you end up with stuff in this column that should be assigned to you, like, oh, I've made a mistake. I forgot that this is a rotating mass. Let's go back and correct these equations, and then this will resolve back to zero. Okay. Now we're going to take the derivative of energy, or not dissipative energy, just potential energy. The potential energy with respect to position. And now kinetic energy is not a potential energy, so those are zero. And then this one resolves itself to KL squared theta is what it resolves to if you do that derivative. This next one resolves to negative M1GL theta, positive M2GL theta, and that's zero. Okay, so I expect you to all be able to do that type of derivative, not just memorize it, be able to do it. If you have questions or problems, go ahead and ask in class or come to office hours, and we'll do that derivative together. But we've done it in class, so I'm not going to do it again. So the last one is dr theta dot. Those are not R's. Those are not dissipative energy terms. The only one's the bottom. And this one resolves to CL squared theta dot. Okay, once again, if you want help with that derivative, let me know, and we'll work on it. Okay, so that takes us through step 11. So that went pretty fast. Now what we're going to do is we're going to collect these terms together. Okay. So I'm going to kind of scrunch it in here all in one page. So what we end up with is this first column gives us J, and these are all theta dots. So M1 L squared plus M2 L squared plus M3 L squared theta double dot. Okay, that takes care of that column. Okay, now I'm going to go to this column just so everything's in the order I prefer it. Is CL squared theta double, not double dot, just a single dot, plus KL squared minus M1GL plus M2GL theta. In this case is all equal to zero, okay? And these terms right here, if I was to collect them, that becomes MEQ. Okay, so anything with the double dot in front of it gets added together and becomes MEQ. These terms right here is our CL, oops, not that far, just in front of the dot, the theta dot. This is our CEQ, is CL squared. And this right here is our KEQ. Okay? So there's an example with the Lagrange method. It had a good number of good edge cases, some potential energies, positive and negative. This M2 ends up not counting. If you want, that's just because this energy becomes just mgl sine theta, and you take the derivative of that with respect to theta, that just becomes cosine theta, which small angle theorem takes that to 1, so it ends up not counting because doesn't depend on theta dot, or theta once you've gone through the derivation. Okay, so hopefully that was helpful. Please practice this with your homework because practice is how we get good at stuff. And feel free to ask questions in office hours or in class.